Okay, let's dive right into this. Welcome everyone to today's explainer. We're looking at a pretty fascinating topic straight from the St. Paul Grade 7 robotics curriculum. Specifically, we're zeroing in on Unit 4, which is all about remote control and coordination. Now, if you've ever tried to steer a remote control car, or maybe you programmed a robot, only to sit back and watch it inexplicably crash right into a wall, well, this explainer is exactly what you need. We're going to unpack the actual science of getting a robot to do exactly what we want it to do. And as you'll see, the way we intuitively think robots move, it's often completely different from the messy reality of how they actually operate. Here is exactly how we'll break this down today. First up, the perfect command myth. Second, we'll do a reality check on robot drift. Third, we'll uncover the secret ingredient, which is feedback. And finally, we'll test your robot knowledge. So, part 1, the perfect command myth. We are going to investigate a super common robotics coding error. To really understand this error, I want you to imagine trying to walk 30 feet in a perfectly straight line, but with your eyes completely closed. You'd probably drift left or right pretty quickly, or maybe you'd trip over a chair you had no idea was there, right? Well, robots actually face this exact same challenge when we try to control them remotely. This brings us to the essential question driving the St. Paul Unit 4 syllabus. How can humans and robots coordinate through controls? I mean, it sounds simple enough, right? We have a manual controller, we have a robot, and we want them to work together. But manual control and event handling, which is really just a fancy way of saying how the code reacts to things happening in the real world, require a very specific type of communication. We humans naturally adjust our steps when we walk, but how on earth do we coordinate that same level of continuous adjustment in a machine? Well, that brings us to a massive misconception in early programming. I like to call it the magic command. Let's say you're a student writing code for the very first time. You look at your screen and you type in a single large movement command like move forward 10 meters. The prediction a lot of students naturally make is that this one magical command will automatically result in the robot reaching its exact destination perfectly 100% of the time. You just tell it to go 10 meters, you sit back, cross your arms, and the robot takes care of the whole shebang, right? Actually, scratch that. It doesn't quite work that way. Let's move into part 2, reality check robot drift. This is what happens when perfect code meets the real world. Now, what's really interesting about this is the stark contrast between our expectation and the reality when we actually test that so-called magic code. On the left side of things, we have our expectation. You send that move forward 10 meters command, and in your mind's eye, the robot just travels in a perfect, straight line to the destination automatically. It's beautiful, it's flawless. But on the right, well, this is reality. You see, the motors on a physical robot are rarely perfectly matched. The floor itself might be slightly uneven. And because of this, the robot might have a tiny, practically invisible 2-degree drift. Over a few inches, that totally doesn't matter. But over 10 meters, that 2-degree drift completely compounds and sends the robot way off course. And what if there's a hidden obstacle in the way, like a rogue trash can? Without ongoing checks, that tiny drift ends up with our robot missing the mark entirely and crashing. So let's look closely at exactly why these single commands fail. There are a few major culprits here. First, there's a complete lack of ongoing performance testing. If the robot just executes one single massive command, it isn't testing its own responsiveness along the way at all. Second, there's absolutely no environmental awareness or user input during the movement. The robot is essentially driving blindfolded. And third, there is an inability to handle unexpected physical events. Sending just one command completely ignores crucial student outcomes from Unit 4. A robot has to be able to handle real-world events, and a single blind command simply doesn't give it the chance to do that. Which brings us to part 3, the secret ingredient, feedback. This is how real coordination actually happens. So how do we actually fix this crashed robot problem? Well, if a single command is like walking blindfolded, feedback is basically taking the blindfold off so you can actually see where you're going. In robotics, feedback is defined as using sensor data or position input to continuously check a robot's progress and then adjust its actions during the movement. For our grade 7 robotics learners, understanding this concept is absolutely crucial. It's the vital bridge between human input and reliable robot behavior. Instead of just crossing our fingers and hoping the robot reaches the target, we use sensors, like distance sensors or wheel encoders, to constantly ask the robot, hey, where are you right now? Are you still on course? So the crucial point here is how this loop of coordinated remote movement actually works in practice. Step 1, you send a small incremental movement command, not 10 meters, maybe just 10 centimeters. Step 2, read your sensor feedback. Look at what the data is telling you. Step 3, Adjust your course based on that data. If you've drifted a bit to the left, steer a little to the right. And then, step 4, repeat the whole process until the destination is reached. We desperately need these small increments paired with constant checks to stay on course. It is not one giant leap, it's a rapid series of tiny corrected steps. And this brilliantly illustrates how the real world of programming aligns with our course goals. The Unit 4 student outcomes achieved here are massive. By utilizing this feedback loop, students learn to map controls to actual behavior much more accurately. They use events, or inputs, in this case the sensor data, to logically guide the code. They test responsiveness by seeing exactly how quickly their robot corrects its drift. And ultimately, they vastly improve usability and reliability. A robot that corrects its own mistakes is a reliable robot. It transforms what would be a frustrating, unpredictable toy into an incredibly capable tool. Let's move to our final segment and see how this builds into our last challenge. Section 4. Test your robot knowledge. Applying the feedback loop to new scenarios. Consider this transfer question. If you are remotely directing a robot to navigate a maze, how would you use incremental commands and feedback to prevent it from hitting a wall? I want you to really think about that for a second. If a single move 10 meters command failed in a wide open room, imagine how incredibly fast it would fail in a tight maze. How often would you need your robot to check its sensors? What kind of small increments would you code into the controller to ensure it can weave safely through those narrow corridors? By answering that, you're actively thinking exactly like a true robotics engineer. So keep questioning those magic commands, keep relying on continuous feedback loops, and you'll be well on your way to designing your own highly reliable code. Thanks for joining me on this explainer, and keep exploring.